Welcome everyone to the afternoon session. Our first speaker is Zilin Jiang from Arizona State University. And the title of his talk is Eigenvalue Multiplicity and Equiangular Lines. Let's welcome.
Yeah, thanks for the kind introduction. Today I want to talk about eigenvalue multiplicity and equiangular lines. So let's just jump right into it. So here is an example of equiangular lines in the plane. As you can see, they come from the three diagonals of a regular hexagon. And what's so nice about this set of lines is that the pairwise angle between these lines is 60 degrees. Okay. And here is another example in three-dimensional space. So this is a regular icosahedron. And if you take the six major diagonals of this regular polyhedron, you realize again that the pairwise angle between all those six lines is the same. So in general, we say that a set of lines is equiangular in r-dimensional Euclidean space if these are the lines through the origin where pairwise they are separated by the same angle. Okay? So it's a simple geometric and symmetric object you could study. And naturally, you start to ask about the following question: what's the maximum number of equiangular lines in n-dimensional Euclidean space? And it turns out that this simple question leads to really interesting mathematics. So here is what we know for all kinds of dimensions. So when the dimension is equal to 2, the maximum is indeed 3. So this is the best example you can construct in the plane. And in 3 dimension, 6 lines is the best you can do. Namely the 6 diagonals of a regular hexagon, icosahedron. It turns out something interesting happens here, that if you increase the dimension by 1 and you reach 4 dimension, the answer is still 6. So, by this additional dimension, you don't get anything. And, we figure out a couple of other cases, and here are several other interesting cases where between dimension 7 and 14, the answer is always 28. So if you add 7 dimensions to dimension 7, you don't get anything new. And similarly, something happens with 23 dimension. So you may wonder, if this has anything to do with a sphere packing problem, where we have very effective sphere packing in dimension 8 and dimension 24. And the answer is yes, through these E8 lattice and Leech lattice. And already in dimension 42, we don't quite know the answer. Already there is some open problem out there. So in general, what we can conclude about the maximum number of equiangular lines in Rn is something due to Gerton back in the 70s, who proved that the maximum number of equiangular lines in Rn is at most roughly half times n squared. But to be exact, it's half times n plus 1. By the way, the proof for this is really elementary. You only need to use some basic facts about linear algebra. So if you're interested, highly recommend read about the proof. Fast forward about 30 years later, the Kane realized that you can indeed construct quadratically many equiangular lines in Rn. Okay? So roughly speaking, we know the asymptotic behavior of this maximum number of equiangular lines in Rn. And if you look at these constructions, you quickly realize that as dimension grows and you try to saturate this quadratic bound, the angles between those lines tend to 90 degrees. Okay? So here's a natural question you could ask: what happens if you fix the angles between the lines. You get to name your favorite angle. I don't know, maybe 6 degrees, maybe some other degrees, and you say what's the maximum number of equiangular lines with that fixed angle. And I'm going to use this e sub alpha of n to denote the maximum number of equiangular lines in n-dimensional Euclidean space with fixed angle arc cosine alpha. Okay, so for some technical reason, this, if alpha, which is the cosine of this fixed angle, turns out to be more important than the angle itself. The reason will be more obvious later. And we, before we work, and there's already some, build up to a general conjecture for this number. So again, back in the 70s, Lemons and Sedell showed that if the angle cosine of your angle is 1/3, then the number is 2 times n minus 1 for all n that's at least 15. So when n is small, like up to 14, there are some kind of irregular behavior for this function. But as soon as n surpasses 15, it becomes more regular. It's just 2 times n minus 1. And the same year, Newman showed that unless this 1 over cosine of the angle, which is alpha, is odd, this function is bounded from above by 2n. In other words, it's saying that potentially more interesting case is to look at the case where the angle alpha is 1 over an odd number. So naturally, after 1/3, you would like to think about 1/5. And that's indeed was done by Newman towards the end of the 1980s. And here, roughly speaking, answer is 3n/2. Okay, and again for n large. And things have been quiet after Newman's work until Boris Buch in 2016 kind of revived the interest in this question. And what he showed is that if you fix the cosine of the angle, which is alpha, this function is always bounded above by a linear function in n. Okay. However, the constant may depend on your angle alpha. And soon, 2 years later, Bala, Draxler, Sudakov, and Kivash greatly improved both results. Basically, what they say is that except the case that's discovered by Lemons and Sedell, where the angle is 1/3, this function is always bounded from above by 1.93 n, as long as n is large. By the way, throughout the talk, if you've got any questions, just please feel free to interrupt. Yes. The quadratic. That's really a good question. So what this result is really saying is that if you fix the angle alpha, then when the dimension is large, it's linear. So those examples will never qualify for the as an example for the quadratic bound. So if you really want to look for examples that meet the quadratic bound, you need to look for a fixed alpha and then with low dimension. Yeah. Yeah, it grows dramatically, yes, which I will talk about later. So some exceptional behavior happens for low dimension, and then once you surpass some threshold in dimension, the behavior of the question is more regular. And we want to understand the regular behavior, because the exceptional behavior, although it's interesting on its own, it's more sporadic. Any other question? Okay, so as you would guess that, for general alpha, let's say alpha over an odd number, say 1 over 2k minus 1, you may guess, according to the pattern, it's roughly k times n over k minus 1. Okay. So when k is equal to 2, this conjecture corresponds to the Lemon-Sedell result, and when k is equal to 3, i.e. the cosine of the angle is 1 over 5, you get 3n over 2, give or take. And certainly the next case is when alpha is 1 over 7. And Newmile already in his paper said that for 1 over 7, it requires a new insight. Okay, here's a question again. And with Polyansky, we gave a very general conjecture for this function. Again, it looks the same. However, here k is a quantity dependent on lambda, which is itself is just a rational function of alpha. Okay. So let me tell you about this k of lambda. So the k of lambda is called spectral radius order, given this number lambda. And the way you get this number is to say, let's go through graphs from the smallest to the largest, one by one. Okay? And for each graph, you calculate the spectral radius of the adjacency matrix. So you write down the matrix representation of your graph, and you calculate the largest eigenvalue, the words spectral radius, quite lambda. And as long as this spectral radius is equal to lambda, you say stop, and count the number of vertices in the graph, and that's your spectral radius order. Okay. So let me give you a couple of examples. So in this table, I listed, the typical value of alpha, 1 over 3, 1 over 5, and, the one that was open, 1 over 7. And you plug in that formula over there, which is a rational function that gives you lambda, you get 1, 2, 3. Okay? And you look at graph G, which consists of one single edge, and you calculate the spectral radius, it's equal to 1, and that's the smallest one. So k is equal to 2, since it has 2 vertices. And similarly, a triangle is for lambda equal to 2, and a complete graph on 4 vertices gives you lambda equals to 3. And therefore, the spectral radius orders of these for these parameters is 2, 3, 4, and conjecturally, we think this function behaves like 2n, 3n over 2, 4n over 3. So already here you can see that this problem has something to do with spectral graph theory, meaning a subfield of graph theory that studies the eigenvalues of graphs. And after we conjecture this result, Polyansky and I got into action and tried to prove it. But the best thing we can prove is for all lambda that is at most root 2 plus root 5. Okay. So you can translate this as this range for alpha, but I will use lambda as the main parameter to describe the result. Exactly. You're quick in your calculation. So root 2 plus root 5 is just slightly above 2. It's about 2.058. Okay, so indeed, our result can recover these two cases, but not the next case, 1 over 7. So here you can, you think about it as a number line, and you plot a dot whenever a graph, hits the spectral radius on that number. So that 1, that's root 2, this is 4. And, our result shows that there is a barrier that needs to be broken, needs to be overcome before you prove anything new, okay? And here's the team when I was a postdoc at MIT. So back then I was still a postdoc. I think then was a graduate student of Yufei, who was a faculty at MIT. and Yao Yu and Zhang Shentong are undergrads at MIT. And what we managed to do is to overcome this barrier. And not only we proved what's conjectured, but also we precisely give a formula for this function whenever the dimension is large. Okay, given that the spectral radius order is less than infinity, so in particular, say when alpha is equal to 1 over 7, in which case lambda is equal to 3, the answer is 4 times n minus 1 over 3 rounded down for all large dimension. And in case you have some alpha which doesn't, for which lambda doesn't correspond to any spectral radius of any graph, then k of lambda is equal to infinity, in which case we conclude that this is n plus little of n. So yeah, any question about the main results? Okay. So again, here's the result and the definition of a spectral radius order. So a couple of remarks. When k, the spectral radius order is less than infinity, our result gives this formula which holds for large n. And from the proof, we really need very large n. It's about 2 to the 2 to the k to the 1 plus little of 1, and pretty large. Mainly the reason is that in our proof, we use Ramsey theorem, which is not really effective for the purpose of lowering the threshold in the dimension. Later, Bada showed that you don't need 2 to the k, but only 2 to the k to the c times k. It's an improvement of the result by a little bit. Conjecturally, we think n can, the threshold for n is just polynomial in k, okay, but that's not known. So that's certainly some problem to think about. Yeah, questions? Oh, yeah, it is dependent in the sense that k depends on lambda, which depends on alpha. And two different, yeah, and it should depend on, because otherwise, if your threshold is uniform, then you will get a contradiction with the quadratic behavior if the angle is not fixed. So the threshold has to increase. That's true. That's true. That's true. Yeah. So the spectral radius order depends on lambda, which depends on alpha. Okay, so already, here's something to think about. And when k is infinity, this should be little of n, which is the low order term. And out of the proof, we know that it's n over log n. And later, Childcrat constructed some example which shows that the lower order term has to be at least log d, or log n. So, again, one can ask to improve the upper bound, even in the case where k is infinity. So let me explain the connection to spectral graph theory. So originally, it's a purely discrete geometric problem. It concerns about lines. Where does graph from? Well, if you are given a set of lines in Rn, which is pairwise separated by angle r cosine alpha, you can represent each line by a unit vector that points in the direction of the line. And when you translate the angle condition or restriction on the equiangular lines, for the unit vectors, they correspond to this restriction on the pairwise inner product. The pairwise inner product now has to be alpha or minus alpha. And the reason that you can get a minus alpha is because suppose you have two directions, certainly for one direction, you can also choose the opposite where it still represents the same line, and the inner product just flips the sign. So you get alpha minus alpha. And you can encode all of this information into a graph. Okay? And the graph goes as follows. You take all the vectors and you connect two vectors as vertices, and you connect two vertices with an edge if the inner product is minus alpha. Okay, so you can now go back and forth between a graph and the unit vectors. So the graph. Oh, the non-edges then represent the plus alpha. So the graph, the edges of the graph encodes the negative inner product, whereas the non-edges encodes the plus alpha. I'm saying that alpha itself is a global parameter that's fixed, right? So your graph only needs to encode which pair, gives you inner product minus alpha, and which non-pairs, the non-edges represent pairs that gives you plus alpha. Yeah. Question. The vertices are the unit vectors within a product, yes. Yeah, but okay, so here, this if and only if is a little bit rough. Let me just, say a bit more about, certainly this graph needs to carry more information than just the edges. Okay, so you see that, okay, maybe let me do it in the following way. So once you have these unit vectors, you can form something called a Gram matrix. That is equal to, the inner product of these unit vectors. And if you write them down, what you see is that because it's unit vectors, so the diagonal entries are all one, where the octal diagonal entries are, those pairwise inner product, which gives you plus minus alpha. And if you use a graph to encode where this minus alpha appears, you can certainly rewrite this Gram matrix in terms of the adjacency matrix of the graph. Okay, and it turns out that this is exactly how you would write down the Gram matrix. And for Gram matrix, we know that it has to be positive semi-definite, and also because we are looking at unit vectors in n-dimensional space, the rank has to be at most n. Okay, so these are the two conditions that you have, and then you can go back and forth between graphs and those unit vectors, as long as the graph satisfies these two spectral properties. Okay, so maybe let's think about example where alpha is equal to 1 over 3, then this is 2 over 3 times I minus, give me one moment. Sorry, so here there's a typo. I want alpha equals 1 over 5. So when alpha is equal to 1 over 5, this is 4 over 5 times I minus 2 over 5 times A of G plus alpha times J. Okay? And in this case, if you, question? Oh, sorry. So yeah, so I need to explain. So this I is identity matrix and J is the all one matrix. So all the entries are one. And the reason we need it is to make these alpha entries. So when alpha is equal to 1 over 5, should be 1 over 3, and you take this n over 2 copies of triangles as your graph. For triangle, the largest eigenvalue is equal to 2. So already you can check that the sum of the first two terms is already PSD. Okay? And the O1 matrix J is also PSD, so the sum will be PSD already. And then you can also check the rank is at most n. Okay? So I'm just giving you an example of such a graph that satisfies these two conditions. And in general, what you should do is to have some alpha, let's say 1/7, and then remember, go through that process, calculate lambda, find a graph G whose spectral radius is equal to lambda, and take appropriate number of copies of that graph. So for 1/7, we should take appropriate copies of a complete graph on 4 vertices, for example. So this example actually generalized so that you get a lower bound for the size of G. And they give you in turn, they give you a lower bound on the maximum number of equiangular lines in Rn. Question? Yeah. Number of vertices, yes, yes. So hopefully I try to give you the impression that that example can generalize so that you get a lower bound on this function E alpha n. As for the upper bound, here is what roughly goes on. So we have this, again, this spectral condition, and I call this matrix M. And by rank nullity theorem, we know that the order of my matrix M, which is say this function, is bounded by the rank of M plus the nullity of M. But the rank of M is bounded by N, so that's at most N plus the nullity of M. Okay, and what's the nullity of M? Well, the nullity of M is bounded by the nullity of the sum of the first two terms plus 1. Okay? So this J only contributes to at most 1 to the nullity. So here we have a situation where we want to understand the nullity of this matrix. Okay? And because this matrix M is positive semi-definite, so if I set lambda to be 1 over alpha, 1 minus alpha over 2 alpha, then this lambda can only serve two roles. Either it has to be the largest eigenvalue of G, in which case this nullity can be reasonably controlled and we can match the lower bound. Or this lambda has to be the second largest eigenvalue of a kinetic graph G. And since we conjectured previously the construction serves as a tight lower bound, we really need to exclude the second possibility. We want to exclude the possibility that lambda, this 1 minus alpha over 2 alpha, is a second largest eigenvalue of G with high multiplicity. Okay, by high, I just mean the multiplicity is, we want to rule out the possibility that the second largest eigenvalue of G is lambda, and the multiplicity is linear in the order of graph G. And another ingredient here is this idea of switching. So remember I told you about this option to select a direction of the line or the opposite of it, right? So in turn, you can have the option to choose a vector v representing a line or the negation of that. And in the work of Bada et al., they show that you can always do this smart way, do the switching so that the maximum degree of your graph is bounded by a constant that depends only on alpha. Okay, so it doesn't, this upper bound delta doesn't depend on the dimension. So in a sense, you have this kind of canonical way of representing equiangular lines with a graph G that's bounded in degree. And what we managed to show is that as soon as you know your graph is connected and bounded degree, then the second largest eigenvalue multiplicity is sublinear in n. By sublinear, it's, I mean constant times n over log n. Okay. Any sublinear bound will already help us to prove the equiangular line result. But in particular, we have this upper bound, which isn't good enough. So let me, elaborate a little bit on this eigenvalue multiplicity result. So the first thing you notice is that you really need the second largest eigenvalue. Here is an example, you can generalize it, where the smallest eigenvalue has linear multiplicity. Okay. So you really need to specify, it's not that every eigenvalue has to have sublinear multiplicity. The second example here illustrates the necessity of connectivity of the graph. So if you have triangles or any graph and you repeat it a couple of times, then the second largest eigenvalue will have linear multiplicity. And lastly, there's something called a strongly regular graph in graph theory that gives you really high multiplicity in the second largest eigenvalue. But the problem with those examples is that they are not of bounded degree. So these conditions turns out to be crucial, otherwise the theorem fails. Certainly, you may ask whether this is the right bound on the multiplicity. So Heyman et al. Constructed some graphs where the second eigenvalue multiplicity is at least constant times root n over log n. So we don't quite know whether this n over log n is really the best you can do. And in the same work, they also try to construct really symmetric graph, which is known as a Kelly graph. And the second eigenvalue multiplicity of those Kelly graphs they constructed is at least n to the 0.4. So root n is indeed the barrier. Yes. We think that certainly, it will be already interesting to prove any polynomial upper bound, say n to the 0.99. But hopefully, we can get it all the way down to n over half, to the half. Any question regarding the statement of the eigenvalue multiplicity? Okay, no. So I'm going to give you a proof sketch of this this result, which I think is quite fundamental for spectral graph theory. So if you are familiar with the subject, normally in spectral graph theory, people would like to talk about some bound on the second largest eigenvalue. There is a study of spectral graph for graphs, and it has to do with mixing of graph and expander graphs. However, this multiplicity result is less looked at, but certainly, it really shines in this in the application of equiangular lines. So here's a proof sketch, right? So we want to prove this result where we have a graph G, it's as bounded degree, and also now we want to bound the second largest eigenvalue multiplicity. I'm going to just write some constants that will be used later. Don't be bothered by them now, but later they will play some role. Okay, so here the first thing you do is to take this graph G and then remove an R-net. So what is an R-net? In analysis, I hope you've heard about this epsilon net, which means that every point is within epsilon distance from a point set, right? So you're casting a net in your metric space and it kind of capture all the fish. Okay? Here R-net is similar, which means that you cast out a net of vertices in your graph so that every vertex in the graph in your graph is within distance r from one of the points in the net, hence the name rnet. Okay, so kind of they are like the kind of guards that you sent out graph. Okay, and you kind of their role is to say whenever you want to visit them, the guard says no, you cannot. So those vertices are now removed, and the rest of the graph is called H. And what happens with this is that once you remove this rnet, the radius of S balls, by S balls I mean a ball of radius S. So in H, you take any vertex and look at the graph induced on vertices within distance S. Okay, S is the number I specify over there. Then what you realize is that the spectral radius of all these S balls drops is now bounded away from lambda. Therefore, the kind of the overall idea is that vertex removal really lowers your spectral radius locally. Epsilon is a constant depending on C. Yeah, not in N. Yes. Yeah. One rnet. Yeah. Just take one. Yeah. But the size of the rnet grows with N, but sublinearly again. So we will use this fact later. Okay. Yeah, so I'm not going into detail here, but assuming these two, we can now bound the multiplicity of H via a moment argument. So here is how it goes. So let's look at the multiplicity of lambda in the graph H. I'm going to multiply this quantity by lambda to the 2s. So certainly this is 2s moment of some of the eigenvalues in my graph lambda. So that's certainly bounded by all the eigenvalues of H raised to 2s, just because this is part of this. It's the same as. Same as, yes. We will use this s soon, okay? So this then is the trace of the adjacency matrix of F as raised to 2s. So probably you already know that if you have a matrix and you raise to case power and take the trace, then that's the sum of the eigenvalues to the case moment of the eigenvalues. But this actually has a combinatorial meaning. It counts the number of close walks in H of length 2s. You start from vertex and you go out and walk for 2s steps and you come back. Such, count the total number of such close walks, that is precisely the meaning of the trace. But then you can say, let me look at all the vertices in H as my starting point. And turns out that the number of close walks in H starting at vertex V of length 2s is precisely bounded by the spectral radius or the largest eigenvalue of the radius S balls around V in H. Okay. Hence, in this case, I can use the second bullet point to the power of 2s. Sorry. So hence, I can use the second bullet point to show that that is at most, let's say, I bound the number of vertices by n, which is already generous, but then this is lambda minus epsilon to the 2s. And by this proper choice of R and S, we can conclude that the multiplicity of lambda in H is little of f. It's by dividing and use approximation. Right. Okay. So finally, we can use a really powerful result called the Cauchy interlacing result that says, sorry, here should be H. So the multiplicity of lambda in G is bounded by the multiplicity of the same number lambda in H plus the number of vertices you removed. But the RNet can be bounded by the number of vertices in G divided by R, or R plus 1. That's another result that you can show. Therefore, together, it's little of n. And that's the punchline of the proof. Yeah, question? Yes. It's again, okay, roughly speaking, you can, it's, okay, the proof itself is already really short. So like, for that step, what you need to argue is that because, spectral radius has to do with walk of length 2s. So originally, before you remove the RNet, you have this walk, these walks that can walk freely. But now, since you cast the net and remove them, so one of the original walk that was there in G now is no longer available, because there is a guard that's within distance s from your starting vertex V, and now you can walk there and wander around and come back. That close walk no longer exists. Hence, results in a drop in the spectral radius of these balls. Roughly speaking, that's the spirit of, and that's what it connects to this, removal of vertices. That's right. Yeah, think works is really crucial in this kind of estimates. Okay. All right. So again, this and here's a natural question. Can you improve on this n over log n? Maybe you care about Kelly graph or representation theory. Then you may ask about the second eigenvalue multiplicity for Kelly graphs. In particular, if your Kelly graph comes from abelian groups, then already work by Gromov, Coding et al. Showed that the second eigenvalue multiplicity is bounded by constant. So that really means that if you want to get high second eigenvalue multiplicity, you are looking at really non-abelian groups. Okay, so a natural extension of the question is to look at unit vectors such that pairwise inner products are either alpha beta, replacing minus alpha by beta. And you wonder how hard could that be? It turns out that it, again, leads to some other interesting mathematics. Okay? So I will briefly talk about this. Oh, yes, that's, yes. So let me mention that it's work by Shratava and Mechanis, I think. And what they showed is that for regular graphs, you can improve the current n over log n to n over log n. And for irregular graph, my understanding is that they don't have improvement. So let's take a look at this, generalization of the equiangular lines. Again, you have unit vectors. Now the inner products can assume two values, beta and alpha. And Boris Buch already showed that, again, it's linear once you fix alpha and beta. And you naturally ask, what's the limit as the dimension goes to infinity? What's that symptotic between? Yes, sorry, this is the end exam, yes. And the conjecture is that now this limit depends on a quantity. So notice, there's a little p down here. is some quantity, but the quantity is defined in terms of sign graphs. So by sign graphs, I mean graphs where each edge can carry signs, either it's positive or negative. Okay? And again, the corresponding adjacency matrix is called signed adjacency matrix, where the off-diagonal entries can be 0 or plus minus 1. And it turns out that we conjecture the limiting behavior of this function depends on two quantities. So this lambda really is just a generalization of previous definition of lambda. But there is another parameter p, which is defined this way. So as you can see, if beta is minus alpha, p is equal to 2. Okay. So we solve this conjecture, which I didn't state, but hopefully I give you the impression of it. We solve them in this problem in two cases. The first case is a joint work with, again, the same group. We show that when p is at most 2, roughly speaking, it's saying that it's equiangular-ish. Okay? Then we know how to do it. The same set of tools still works. Or lambda is equal to 1, root 2, or root 3, some other values of lambda. Oh, here I should say or. So when p is less than or equal to 2, or p is one of those. And the second result by Polyansky, with Polyansky, is to show that whenever this lambda is less than lambda star, which is about 2.0198, and to be specifically, lambda star is root rho plus 1 over root rho, where rho is something known, if you look at Wikipedia, called plastic ratio. So the golden ratio is x squared equals x plus 1. The plastic is x cubed equals x plus 1. I don't know. Silver ratio is something else, actually. Anyway, so it actually turns out that this 2.0198 is, again, now the barrier to this spherical two-distance set. And, I wonder, if people can come up with some new idea. So overall, the framework that we use to prove these special cases is some forbidden local subgraphs, meaning that we try to leverage the condition that the Gram matrix, which I define M, is positive semi-definite. And just by playing around with this positive semi-definiteness, you gain a lot of local insights into the graphs that you built. And second, globally, we know the graph representing this two-distance graph satisfies some really nice properties. So for equiangular lines, as I already explained, the graph can be made bounded degree. Okay? And for spherical two-distance set, it's the following result. So remember the parameter p that I mentioned in the previous slide? If you zoom out and look at the graph far away, you realize the graph itself is a complete p-parti graph. It is. So there's a rounded down. Yeah, rounded down. Yes. So indeed. So p is always integer, where lambda can be various things. Yeah. So if you zoom out, it's a complete p-parti graph. But if you zoom in, you realize that it modifies locally by bounded degree. Okay. So it's an XOR between a bounded degree graph and a complete p-parti graph. So in this sense, we really need new insights in spectral graph theory to move this result forward. So far we are stuck with the case where p is at least 3 and lambda is less than lambda star. And I will give you two reasons why we need some new insights. The first reason is that, remember the second eigenvalue multiplicity result, it's just false for sign graphs. For sign graphs, it fails, and we can construct examples. And in the work with Polyansky, we also noticed that if you only use the first condition, you only try to play this local game, and you try your best to play the local game, it will never break the lambda star barrier that presented in the work. And very recently with Wang Zhiyu, we showed that even with the second result, where you also leverage this global graph structure, you will never break this p at least 3 and the lambda star barrier. Okay, so indeed, we're at a point that we need new ideas. And throughout this process, we have some byproducts. We have some byproducts, and hopefully it may appeal to maybe some number theorists in the audience. And maybe representation theorists. So the first result is a classification of graphs whose least eigenvalue is bounded from above by minus lambda. And if you take lambda equals to 2, it's a classical result by Cameron et al., which actually, they classify all graphs with smallest eigenvalue at least minus 2. And what they used is those root systems and the classification of semi-simple Lie algebra. And what we managed to show is that we managed to push this number a little bit negative in the sense that we replace this 2 by lambda star, which is the 2.0198, etc. So here, it may be more helpful for the spherical two-distance set to understand, to classify sine graphs whose smallest eigenvalue is at least minus lambda star. So that's one question. Here's another question that has to do with matrices. So, if you want to take away some elementary result from this talk, here's one that you can, tell your students in linear algebra. So, in 1987, Vijay Kumar showed that you take any symmetric integer graph that is hollow. Hollow means all the diagonal entries are 0. Okay? And you realize the matrix has some eigenvalue less than minus 2. Then you can always find the principal sum matrix of order at most 10. No matter how large your initial matrix is, you can always zoom in and find the 10 by 10 principal sum matrix with the same property. You see that by Cauchy interlacing theorem, if you already have a principal sum matrix that has an eigenvalue less than minus 2, then the entire matrix has the same property. And this is saying the converse is also true. So it's kind of a compactness result. And inspired by this connection, and actually the connection goes back to the sine graph and the forbidden subgraph of sine graphs. What I managed to show is that I determined all lambda where lambda replaces this 2 such that we can have a similar statement. Okay? And you may guess it, the set of lambda is precisely less than lambda star. So for lambda less than lambda star, this is always true, and it's false when lambda is at least lambda star. So there's a threshold phenomena. A related problem would be to ask the same question for symmetric integer matrix with spectral radius at most lambda. And in connection with Lemon's conjecture, which is a famous conjecture in number theory that says the of any integer coefficient polynomial is either 1 or bounded away from 1. And McKee and Smith had a really nice result that resolves part of the conjecture by thinking about certain polynomials. So in that, on the related note, a related problem is to classify all indecomposable integer symmetric matrices with spectral radius between 2 and 2.058. Okay, so I will end my talk with some other equiangular lines. So here's a really famous conjecture. So you can think about, we thought about Rn, but what about complex number to the n? Equiangular lines over complex numbers. And it turns out that because of numerical reasons, it's highly possible that the maximum number is precisely n squared without any exception. So it's a more regular problem than the problem over the reals. And you can ask the same question over the complex. If you fix the angle, what's the asymptotic behavior of the maximal equiangular complex lines? And finally, you can also think about equiangular subspace, where equiangular lines is just a one-dimensional subspace, but you can think about k-dimensional subspace with pairwise angles separated by the same value. And with that, thank you very much for attention.
All right. Thanks for the wonderful talk. Any questions?
What about if we replace vertices by say pairs? It looks like the last problem you mentioned, the k-dimensional subspace. Yeah. If you only think about the case of 90-degree, it's like a frames, right? Like there is a, well, if I remember correctly, there is a problem in quantum theory says that you want to have the so-called mutual unbiased basis. Right?
MUB.
Yeah, MUB, you know about that.
Yeah.
So is your method applicable to this problem?
Yeah, I think this method is usually about fixing the angle and let the dimension grow. So what I understand for MUB is that look for those more exceptional structures where usually that happens in lower dimension. So I think it's a slightly different problem. Yeah. But maybe the question about MUB is more related to Zona's conjecture in the sense that over there they are looking for SIC POVM. I don't know, the full name for this, but that's the words to look. Yeah.
Thank you.
You're welcome.
Okay. Any other questions? Okay, if not, then let's thank our speaker again.